Shri Gurubhyo Namaha, children. Welcome to our online class Ekalaiva. Today we are going to continue with 12th standard state board syllabus, 4th chapter Electromagnetic Induction and Alternating Current. The subtopic which we are going to do today is AC circuit containing an inductor. Now this is the circuit diagram where an inductor of inductance L. So L represents the inductance value of an inductor. Now this is connected to an alternating voltage source. Now this is the alternating voltage source. To this you connect an inductor of inductance L. Okay, so when such a connection is made, now what is this? V is equal to Vm sin omega t. Now this V is nothing but the instantaneous voltage. Now this equation you are already familiar with. This we have already discussed in our last topic. The instantaneous voltage is given as V is equal to Vm sin omega t. Now here Vm represents the voltage amplitude. Okay, Vm represents the voltage amplitude. Now V represents the instantaneous voltage and omega represents the angular frequency and t represents the time. So this equation you are already familiar with, which gives the value of instantaneous voltage, right? Okay, so when this alternating voltage is applied across an inductor, now this alternating current will flow through the inductor and there is a induced EMF, a self-induced EMF is produced in the circuit, right? Now this self-induced EMF, the inductor will have a self-induced EMF produced in the circuit. This self-induced EMF is otherwise called as back EMF. Now why it is called back EMF is, now this self-induced EMF, it opposes the cause. We have already studied Lenz's law, right? So this will oppose the cause. Now which is the voltage given here? So this EMF is nothing but you call it as back EMF, whose value is given as, now first let me start with the alternating voltage that is given, which is equal to Vm sin omega t. Now let this be equation 1. So what is the value of back EMF produced, which is represented as epsilon, which is equal to minus L di by dt. So what is this L? This L I have already told you, it is nothing but coefficient of self-inductance or self-induction. And you know di by dt is nothing but change of current. Okay, so this is the value of back EMF. Okay ma? Right. So this is equation 2. Right. Now I am going to apply Kirchoff's law to this circuit. Once again let us come back to this circuit. Now in this circuit, now this is the potential given to the inductor. So there is a potential whose value is given as V is equal to Vm sin omega t. Okay, now this will produce a self-induced EMF which is given as epsilon equal to minus L di by dt. So applying Kirchoff's loop rule to this circuit, what is the net potential drop across this circuit? The net potential drop will be the difference in their voltage, difference in the voltages, that is now that is V minus, now what is this back EMF? This is again epsilon. So V minus of minus epsilon will give the net potential difference across this circuit, which is written as V plus epsilon equal to 0. Now this is with respect to Kirchoff's loop rule. Applying Kirchoff's loop rule, the net potential difference in the circuit is equal to V plus epsilon equal to 0. Actually, it should be V minus epsilon, which becomes plus here. So, this gives the total potential difference in the circuit, which is equal to 0. This is by applying Kirchoff's loop rule. Okay. Now, I am going to substitute the value of V and epsilon from this equation. So, let us substitute here. Instead of V, I will substitute Vm sine omega t plus I have for epsilon as minus L di by dt equal to 0. Now, when I take this to the right side, I have the equation Vm sine omega t is equal to L di by dt. Okay, right? Now I wanted to have the value of current. So let me bring this di to the left side. So di equal to, when I rearrange this equation, this will be Vm by L sine omega t into dt. So this is the equation. Is it clear, children? Hope you are understanding the steps up to this. But here also, I wanted to have the value of current. Now here I have got the value of current only for di. So if I wanted to have the value of current, I should integrate this equation on both sides. So when I integrate this, okay, so integrating on both sides, I have integral di. So what is integral di? Integral di is I. Now as far as this side is concerned, this Vm by L is constant. So let me take this out. Vm by L. I am going to integrate sine omega t dt. Okay ma? Now I am going to integrate. I will have the value of I as I is equal to Vm by integral sine omega t. Integral sine omega t is minus cos omega t by omega, right? So I will bring that omega also outside. So in the denominator, I will have Vm by L omega. Now inside the bracket, I will have minus cos omega t plus a constant, plus C. Let me write this as constant. Okay. Now as far as this inductive circuit is concerned, this constant does not have any use because it is independent of time. So we will take this constant value to be 0 and hence we have I is equal to Vm by L omega. Let me bring this minus outside. You will have cos omega t. Okay ma, is it clear? Now I need to compare this current equation with the voltage equation. I have started with voltage equation and I have finished with I equation. Now I am going to compare this. But before I compare this, when I compare this term sine omega t, here it is cos omega t. So what I should do is, I need to convert this current equation, this cos omega t, in terms of sine omega t. Only then the comparison will be simple. So first let me convert this cos omega t in terms of sine omega t. So this cos omega t, now let me write here children. So cos omega t is written as cos theta. Omega t is nothing but theta. Okay. Now angular frequency formula. Now we know omega t is nothing but theta. Right ma? So theta is equal to, we have the formula for theta. So I can write omega t as theta also. Now here the formula for cos theta is sine 90 minus theta, right? So I can write this 90 as pi by 2 children. Pi is 180 divided by 2 is 90. So cos theta can be written as sine 90 minus theta. Theta is nothing but omega t, right? Okay, so sine 90 minus theta, and here I have a minus sign. So I will have minus sine pi by 2 minus omega t. Okay, but I need to remove this minus sign. So to remove this minus sign, I will rearrange this term, because here I will take sine of minus theta will be minus sine theta. So I will take a minus sign from inside. So if I take a minus sign, so minus of minus will become plus. So here I will have sine omega t minus pi by 2. So I can write cos omega t as sine omega t minus pi by 2. Just a small conversion so that I will change the current equation in terms of sine. So let me write the value of current as I is equal to, now Vm by L omega sine omega t minus pi by 2. So this is my current equation, right? Now I am going to compare this voltage equation and the current equation, right? I am going to replace this as, actually current equation is I is equal to Im sin omega t, right? So what is this Im? Im is nothing but Im is Vm by L omega. So I will substitute instead of Vm by L omega as Im, which is considered to be the peak value of the alternating current. What is Im, children? Im is peak value of alternating current. So the equation now becomes I is equal to Im sine omega t minus pi by 2. Is it clear? Is it clear? So now let us compare these two equations. Now let me name this equation as 4. Okay, so let us compare this voltage equation and current equation. Now voltage equation is V is equal to Vm sin omega t. Current equation is I is equal to Im sin omega t minus pi by 2. So what do you conclude from this equation? Now we can know from this equation that current is lagging behind the voltage. Current lags. Let me write here, children. Current lags behind the voltage by a phase angle of pi by 2. So what is the difference between current and voltage in an inductive circuit? In an inductive circuit, current lags behind the voltage by a phase angle of pi by 2. Okay. Now this is also represented in the Phasor diagram. Now let us look at the Phasor diagram here. Now this is the Phasor diagram. Now we have the equations for voltage. V is equal to Vm sin omega t, and the current equation I is equal to Im sin omega t minus pi by 2. So how to draw this Phasor diagrams? By substituting different values of sin theta for voltage and current. Now here this red color line, red color curve, it represents voltage curve, and here the green color represents the current curve. So let us start with voltage. Now I am going to substitute different values for omega t. So what are the different values of omega t? Omega t we are going to substitute. Look at the theta. This is omega t, right? So 0, then I am going to substitute 90, then 180, then 270, then 360. So let us substitute different values for omega t. 0 degree, 90, 180, 270, 360. So let us take this voltage equation first. V is equal to Vm sin omega t. Now I substitute for omega t as 0. Okay, so when omega t, which is along the x-axis, is 0, when omega t is 0, Now what is substitute for omega t as 0? So sine 0 will be 0. So V will be equal to 0. So the voltage will be 0. So this will be the first point. Okay, omega t 0, V also 0. So this is the first point. Okay, which is a cross mark. I'll just put a cross mark here so that you understand better. Next, we'll substitute for omega t as 90. Okay, now 0 and pi, in between you have pi by 2 children. You see this gap is pi by 2. Okay, you forget this current curve for some time. Let us bother only about this voltage curve. So in between 0 and pi you have pi by 2. So substitute pi by 2, that is omega t as 90. Pi by 2 is nothing but 90, right? So omega t is equal to 90. So when omega t is equal to 90, what is sine 90 children? Sine 90 is 1. So 1 into Vm will be Vm. So the value of V is equal to Vm. So where is Vm? So theta omega t is 90 and V is maximum. So imagine this value to be, suppose if it is here, let us imagine that this value is somewhat 8 volt. So in that case, the second point will be here. Okay, so theta pi by 2 and V is maximum, Vm. Okay, ma? Next, you substitute omega t as 180 children. Substitute omega t as 180. In that case, sine 180, 0. Then 0 into Vm will be 0. So V will be 0. So again, the third point is multi theta 180, which is pi. Okay, theta 180, V is 0. Similarly, you mark for omega t, next value is 270. So substitute omega t as 270, sine 270 is minus 1, minus 1 into Vm will be minus Vm. So V will be here minus Vm. So substitute here. Now in between pi and 2 pi you have 270. 3 pi by 2. Okay, ma? So you have the fourth point to be marked here. So minus Vm. Now here it is plus, we took the value approximately as, suppose if it is going to be 8 volt here it will be minus 8 volt, right? So 270 and you have minus Vm here. Okay, ma? And the last value is 360. So omega t is equal to 360. I have once again the value of V to be 0. Sine 360, of course 0. 0 into Vm is 0. V is equal to 0. So this is the fifth point. Okay, ma? So when I join all these points, I will have the curve to be like this. Okay, similarly, I will draw, now this is the voltage equation for which I have drawn the diagram. Now here, now let us consider the current equation. I is equal to Im sine omega t minus pi by 2. Now to draw the current curve. Okay, now here what should you write? Again you are going to substitute the same value, that is 0, 90, 180, 270, 360. But after you substitute, suppose let us substitute omega t as 0. Now omega t is 0, 0 minus pi by 2. Suppose let me explain you this better. Now substitute omega t is equal to 0. Okay, ma? So what will be the value of I? When I substitute omega t is equal to 0, substitute omega t 0 here, 0 minus pi by 2. Pi by 2 is 90. So 0 minus 90 is minus 90, right? You have to take the value of sine minus 90. So sine minus 90 is minus 1 children. So what is the value of I? I will be minus m. So the first point, look at the first point, omega t 0 children. But I is equal to minus Im. So they would have started the graph from here. Okay, ma? So I becomes minus Im. So let us approximate some value here. So you will have, now this is current equation. Now this time you will consider the value of current. That is why you have V and I here. For the previous part we took this y axis to be voltage. This time we are going to take this y axis to be current. So for omega t equal to 0, I is equal to minus Im. So I have substituted, I have marked here. Okay. Now let us go to the next condition where omega t is equal to, what is the next value of theta? Omega t is equal to 90 degree children. Okay. So if omega t is equal to 90 degree, here I will substitute 90 minus 90, 0. So sin 0 becomes 0, then 0 into Im is 0, so I will be equal to 0. So that is the second point. Okay, am I making you the concept clear? No, this is theta. Theta here is pi by 2, I value is 0 here. So second point. Similarly, I keep on marking. Though this is the third point. Substitute omega t is equal to 180 children. Omega t is 180. 180 minus 90 will be 90. Sin 90 will be 1. 1 into Im will be Im. So I will be Im here. So I will be Im. You will substitute here. Okay, see here, for an angle of 180, omega t 180, I will be Im. Okay, similarly, for the next angle, omega t is equal to 270, omega t is equal to 360, you keep on substituting. Now, this is how you will mark the points for the current. Okay, so omega t is equal to 270. Omega 270, in the sense, I will be here 270 minus 90. 270 minus 90 is 180. Sin 180 is 0. Im into 0 is 0. So I is equal to 0. So for 270 degree, the current value is 0. This is the fourth point. Similarly, for omega t is equal to 360, the value of I will be, again substitute 360 here, 360 minus 90 is 270, sin 270 is minus 1, so minus 1 into Im will be minus Im, so I have the value of I is equal to minus Im, once again here 2 pi, okay, for 360 I have minus Im. Okay, so when I plot all these points, this is the graph. Okay, so this is nothing but you call it as phasor curve, right? Now compare. Now look at the phasor curve. Now from this we can very well understand that there is a phase difference between voltage and current. Now current is lagging behind the voltage by a phase angle of pi by 2. Okay, now here is the phasor diagram. Now this is the voltage phasor, this is the current phasor. We have already discussed in our previous videos how to draw these phasor diagrams with respect to voltage and current. Now as far as an inductive circuit is concerned, as we discussed now, the voltage always leads current by pi by 2, or the current lags voltage by pi by 2, right? So here this is the voltage phasor. Now this length is nothing but Vm, maximum voltage amplitude. Now this is the current phasor, and the angle between them is pi by 2, because the phase difference between them is pi by 2. So the angle between them is 90. Since the current lags behind the voltage, the current phasor to be drawn here. So this phasor diagram clearly depicts that the voltage leads current by pi by 2, or the current lags by pi by 2, minus pi by 2. Okay ma, so this is Im sin omega t minus pi by 2. Here you have Vm sin omega t. Hope you are very clear with the graphical representation of phasor diagrams for the current and voltage values here. Now next we are going on to a very important concept called inductive reactance. So once again let me write the current equation. I is equal to Im sin omega t minus pi by 2. So this is the current equation, and I said the value of Im to be, what is the value of Im? Im is Vm by L omega. Now let us compare this equation with the current equation in the resistive circuit. So what is Im in case of resistive circuit? It was found to be Vm by R. Okay, this is with respect to a resistive circuit. Okay, now in this resistive circuit, R is nothing but the resistance. Hope you are all familiar with all these things. I just wanted to recall. So R represents resistance. Now this is with respect to a resistive circuit. Now when I compare this value of R to the value of current in this inductive reactance, now this L omega plays the role of the resistance in the resistive circuit. Yes or no? Now here numerator you have the same value which is Vm, but denominator this L omega plays the role of the resistance in a resistive circuit. So this L omega is named as inductive reactance. Inductive reactance, which is represented as X suffix L. So L represents inductor circuit. So this L omega is nothing but you call it as inductive reactance. Okay, and the unit for this inductive reactance, okay, now it is also measured in ohm, because here now this is compared to the resistance in a resistive circuit. So the unit of resistance is ohm. Similarly, the unit of inductive reactance is also measured in ohm. But there is a small difference. Now here you say it as resistance. Resistance means it is resistive. But here you name the term as inductive reactance. Now what is this reactance? There is a small difference between this. Now whenever we consider a circuit, whenever we consider an AC circuit, AC is alternating. Now for an alternating current you have what is called as frequency. Okay, now in a resistive circuit, now this resistance value is independent of frequency. It does not have any influence on the frequency. If there is change in the frequency also, the resistance value will not be changing. Okay, it remains the same. There is no effect if the frequency is changing. As far as a resistive circuit is concerned, the resistance remains the same. There is no change. But whereas when you consider a inductive circuit, now when the frequency is changing, now here it will react. In an inductor circuit, if there is a change in frequency, there will be a reactance in the circuit. It will react. This will also vary. So if this is varying, you call it as, that's why you call it as reactance. It will react with change in the frequency of AC. Whereas in an AC circuit, if there is a change in frequency, the resistance will not have any influence. Whereas in an inductive circuit, if the frequency is changing, here also there will be a change, and hence you name this as reactance, and you name it as inductive reactance. Okay, now let us move in detail with this. We will have the formula inductive reactance XL is equal to what is the formula? Omega L. So what is this omega? You know the formula for omega, which is angular frequency. What is the formula for omega is 2 pi f, right? Now substitute. XL now becomes 2 pi f into L. So this 2 constant, pi constant, L is also constant. So XL purely depends on frequency. This is what I said. Definitely this reactance has got a dependence on the frequency of the alternating current. Since the current is alternating, definitely you have a frequency which makes this value to be changing. So you call it this as inductive reactance. Suppose if it is not a DC, look at this once again, this circuit. Instead of an AC here, if I am going to connect a DC, so what happens here? If I am going to connect a DC, as far as DC is concerned, you don't have the value for frequency in a DC circuit. In a DC circuit, F is 0. So you have the value of XL to be 0. So XL offers no resistance to DC current, which means in an inductor circuit, an inductor allows DC to pass through it. So that is the meaning for this. In an AC, that's in an ideal inductor, what does it do is, it offers no resistance to steady DC current. So this is also one more conclusion we learned from this topic. Okay, so this is about AC circuit containing an inductor. Okay, we are going to learn more about this AC. We are going to have the next video containing AC containing only a capacitor. So what are the changes that will take place? That also we are going to learn. And to subscribe for our online classes, please press the subscribe button and you will be receiving our latest updates. Thank you, children.